Imagine a team where some members become so dependent on each other that, if one person is absent, the whole team struggles to perform. This exact challenge can arise in neural networks, where certain neurons or features might become overly reliant on others. This over-reliance leads to a lack of robustness, especially when the network encounters new, unfamiliar data. It is a common problem in deep learning that can hinder a model's ability to generalize effectively. So, how does Dropout prevent this feature co-adaptation? Dropout prevents feature co-adaptation by randomly deactivating a proportion of neurons, along with their incoming and outgoing connections, during each training iteration. This means that, during every single forward and backward pass, a different subset of the network is used, forcing individual neurons to learn more robust and independent representations. The core mechanism behind Dropout's effectiveness lies in its ability to introduce noise and uncertainty into the network's training process. By randomly dropping out units, the network cannot rely on any single neuron or specific set of neurons always being present. This forces each remaining neuron to become more self-sufficient and to contribute independently to the overall prediction. Think of it like a group project where you do not know which teammates will show up each day. You would learn to handle different parts of the project yourself, ensuring that the project can still be completed even if key members are missing. In a neural network, this translates to neurons learning to extract features that are useful on their own, rather than relying on a specific combination of other neurons to activate in a particular way. This redundancy in feature learning is crucial. Without Dropout, neurons might develop highly specialized roles that only make sense in conjunction with other specific neurons, leading to brittle dependencies and a phenomenon known as feature co-adaptation. When this happens, if one of those specialized neurons is not ideal for a new input, the whole carefully constructed dependency chain can break down. Dropout breaks these dependencies. Practically speaking, this process encourages the network to develop a diverse set of internal representations. Instead of relying on a few strong interconnected features, the network learns to use many weaker, more general ones. This directly translates to improved generalization performance on unseen data, because the model is less sensitive to specific patterns in the training set and more capable of handling variations in new inputs. It effectively builds a more resilient and adaptable model. A fascinating aspect of Dropout is how it approximates an ensemble of exponentially many different neural networks, all sharing weights. Each time you train with Dropout, you are effectively training a unique, thinned network. Because these thin networks share weights and are sampled from the same original network, they average their predictions implicitly. This ensemble effect is incredibly powerful, allowing the single Dropout network to achieve performance comparable to training and combining many individual models, but with significantly less computational overhead. It is like getting the benefits of a large committee of experts by just randomly shuffling a single group of people each day. Ultimately, Dropout is a remarkably clever and powerful regularization technique. By dynamically disrupting the internal collaborations between neurons during training, it compels the network to discover more fundamental and broadly applicable feature detectors. This systematic prevention of overspecialization and co-adaptation results in a neural network that is not only more robust but also significantly better at generalizing from its training data to the complexities of the real world.